Here we go. Open up to page 4. We're going to do the second part of your notes today. We're going to go a little bit more in depth on the computer printout. So let's do that. Including talking about some of the basics of statistical evidence of a linear relationship. Okay, kind of start this idea of statistical evidence. So on page 4 in your packet, here we go. So where is the data that the equation of the line comes from in a computer printout? Coefficient, very good. So here is our values for your least squares regression line. Your line of best fits, good. Constant versus this second thing that's the variable. Constant is going to be your what part of that equation? Your y-intercept, it is the one without a variable. So this entire line is about y-intercept, okay? This is the value of the y-intercept, negative 87, and then we'll talk about the other things about it as well. So the second one is the variable height, and the coefficient to the height is the m, or the slope. So this entire line is about slope. All right, now, a couple things. Let's first talk about your y-intercept. Interpret the y-intercept. It happens when the x is 0. So if this is about volume and height, say, imagine this is about trees. Oh, it is. It's analysis of trees. So if the height is 0, what is that saying about the volume? If the height is 0, it's negative 87.12, okay? And what do I say about the y-intercept? It often does not make sense. Okay, now here is an example of how that occurs. So let's look at this picture real quickly of height versus the volume. So probably what's going on is we are collecting data out here in this vicinity of height. So our data is out here, our trees are out here. And so, sure, we can see that there is a constant rate of increase in the volume. Okay, so in that section, it is linear. But we do not know if that linear model will continue outside of our data. It could level off. It may continue in a linear model. It may level off. So what happens is this y-intercept is based off of the idea that the linear model is continuing all the way out there to where x is 0. But you know what? Probably, does it follow a linear model that whole way? Probably not. It probably is going to level out and get yourself an asymptote or go down to 0 right there. Okay? So that is why you get a y-intercept. That's the reason that you get a y-intercept that sometimes doesn't make sense, because it's under the assumption that the linear model continues all the way out to the y-intercept. When you are trying to make a prediction outside of the data, that is called extrapolation. So technically, your y-intercepts are frequently extrapolation. That's another reason, that's why they are not making sense a lot of times. Okay? All right, so just kind of reminding you of that vocabulary word. Now, let's talk about this next little column. This SE coefficient means that it is the standard deviations of the y-intercept and the slope. SE stands for standard error, because it's observed minus expected. It's how far your observed is away. They call that an error because your observed is not expected. So that's really your standard deviation coefficient. This is the t-score. If we were to run a test for the value of the if there's a y-intercept or if there is a slope, if we were to run a test against the y-intercept being 0 and the slope being 0, these are the t-scores. So these are the t-scores that you would get, and these right here are the p-values that you would get if you were going to run a test for the y-intercept or for the slope. Now, if the y-intercept frequently doesn't make sense, are we interested in finding out about it and running a test about the y-intercept? No. So we pretty much don't care about this data here because we're not interested in running a test for the Y-intercept. It frequently doesn't make sense, so we don't even care about what that is. But slope stuff we are very interested in. So let's first talk about the standard deviation of the slope. Okay, we've addressed that before. That's this value here, 0.3039 or 38. This is often represented by S with a little b. Standard deviation of the slope. Standard deviation of the slope. So let's review what that is. What is the standard deviation of the slope saying? Yes, it kind of has to do with, well, not exactly residuals, but how far off that slope, the variability in the slopes from sample to sample. If Lauren went and got 100 trees in the forest, and Thomas went and got 100 trees in the forest, and Jake went and got 100 trees in the forest, and I went and got a random sample of 100 trees in the forest, we're all going to then run our own little linear regression, and we'll all get different equations. Why? Because of sampling variability, good, and our slopes are going to be a little off from each other. Now, I'm interested in how far can our slopes be off from each other and be reasonable. See, I want to know that. So I want to know, having equations that are like this isn't going to totally throw me off. I'm not going to freak out if you get this equation right here. Because these slopes can be off. If we sample many times, I expect the slopes to be off on average about that 0.38 or whatever that number was on there. Okay, so that tells me that our slopes can be off about 0.38 or whatever from each other, and that's reasonable. That does not freak me out. But say somebody comes and gets this thing right here, then I'm going to freak out because that is a heck of a lot more standard deviations away from the rest of all of those. Okay. So in summary, you'll know that if you sample many times, I'd expect the slope you find of the relation between height and volume to vary this much on average over time. So if you sample many times, I'd expect the slope that we get of the relation between those to vary about that much on average. Okay, so that is your interpretation of standard deviation of the slope. Now, let's do standard deviation of the residuals. That is not found in this first set of data. Where do you find standard deviation of residuals? Right here, this plain little s is standard deviation of the residuals. It is also frequently listed as S with a little e for standard deviation of the errors. The residuals are frequently called the errors. So that is the standard deviation of the residuals. Okay. So let's say you get one tree and you want to see how far it is away from predicted. And it's 15 feet off, or 15 cubic feet. The volume was predicted to be a certain thing, and it's 15 cubic feet off. Are you going to freak out if your tree is 15 cubic feet higher than expected? Are you going to think, oh my gosh, this is a mutant tree? This will let you know. This is 13.4. So 15 cubic feet, what does that tell you? How much is that off? Just a little over 1 standard deviation of the residuals. Are you going to freak out about a 15 feet residual? Probably not, because look at this picture here. Here is your prediction line. Trees that are along this have a predicted volume. That was the actual is the same as predicted. Okay, here, actual volume was the same as predicted. But these ones up here are within 1 standard deviation. That's 13.4 cubic feet above predicted and 13.4 cubic feet below predicted. Okay? And then 2 standard deviations would be 26.8 cubic feet and 26.8 cubic feet below. So don't forget that of all of your 100 trees, you expect about 68% of them to be within 1 standard deviation away from that prediction line. Okay? And then 95% of them will be within 2 standard deviations of predicted. Okay? And then, of course, the third one is the how much for the third one? Do you remember that? 68, 95, 99.7. Okay? 68, 95, 99.7. All right, so that is what's going on in your standard. So standard deviation of the residuals is the average amount that the actual y value point varies from what's predicted to become, varies from the predicted y. Okay, so if we go back here and we look at our words for that, let's see here, where are we? There it is. So right here, the average amount that the actual volume varies from the predicted volume. The average amount that all of those actuals are varying from the predicted y values. All right. Okay, very good. So that kind of takes us through most of that. Now, let's not forget that when we find r, it needs to be the square root of the r squared value. But how do I know the sign that it should be? How do I know positive or negative? Good. Positive or negative is based on the slope being positive or negative. Okay. Now, last thing. This very last thing that I want to teach you on this is really the very start of this chapter's running a test for the slope of the relationship between two items. So I'm going to do this in a different color because it's really the new stuff that we haven't talked about yet. So first of all, let's talk about a parameter called beta. Beta is the variable that we will use for the population slope. So this is the slope of the relationship between height and volume for this problem. Okay. So beta is the slope of the relationship between height and volume. And we will run a statistical test so that we can get statistical evidence to see if there's a linear relationship or not. So what we do is say our null hypothesis is that beta equals 0. And if the slope is 0, what does that say about this linear relationship between height and volume? There's not one. So if your slope is 0, that essentially says there is no linear relationship between height and volume. Okay? Our alternative hypothesis would say what? That beta is, we'll just say not equal to 0, because I don't know which way it's going. It's probably going to be positive, but not equal to. And so if I find that I have a slope, then I have got a what? Linear relationship between those two things. So slope being 0 means no linear relationship. Slope being something means I have a linear relationship. And then guess what? Your statistical evidence comes from your what of the test? P-value. Can you tell from R? No, you don't know. Residual plot. You must check. Look at the residuals and see if there's a pattern. Statistical evidence only with this P-value. So this is statistical evidence of a linear model based off of this p-value. If this p-value is 0, what are you going to do with the null hypothesis? You will reject HO. And if I'm going to reject HO, I'm rejecting that there is no linear relationship, and I can say I have statistical evidence that there is a linear relationship. Okay, so that's the basics of the general gist of what this linear regression test does for us. So now let's just kind of go on to what your homework's going to do. Let's go ahead and talk through what I want you to do on your homework. So go on over to page 6. Your homework is pages 6 through 8 and then page 10. Pages 6 through 8 of your packet. Page 9 is blank because we're going to draw on it tomorrow. Page 10 is the start of the next section, but I think you can do it. I'm going to talk to you about it today. So here we go. On page 6, you're essentially doing this stuff right here. This is a problem. I'm going to start you with a little bit because I kind of want to give you a hint about part C. This is about men participating in a study. They agreed to the relationship between several variables, including height, weight. This is not the correct waist. And percent body fat. Okay? But it is corrected down here to be the middle of your body, your waist. Okay? So we're talking about the relationship. So real quickly, let's write the equation of our regression line. We are going to be predicting what? What is our... Nope, we're not predicting waist size. Waist size is our x variable. Percent body fat. See, I can see right here that the dependent variable is my percent body fat. So I will be predicting my percent body fat from the waist size. So what are my numbers here for my equation? Slope 1.7 times your waist size, spell that correctly, and then minus 42.73. Okay? The reason I want to hit that there is so that we can talk about part C. You'll do part B also, so don't skip that. You'll come back and do that. But let's look at C. One of the men who participated in the study had a waist size of 35 with a 10% body fat. Calculate the residual associated with this person. So how do I compute a residual? Good. Residual RAP. R-A-P. Residual R equals actual minus predicted. Actual Y minus predicted Y. Actual Y minus predicted Y. So this information, a waist size of 35 and a 10% body fat, what is that? That's what actually occurred. So he actually had an X of 35 and a Y of 10. So that's his actual 10. How do I get his predicted body fat? Good. You will plug 35 into your prediction equation to get the predicted percent body fat. And once you get this predicted percent body fat, then you can subtract and have your residual. Okay? Remember how to do that computing. Okay. And then number 2 and 3, just make sure when you write these equations, do those in context. Okay? When you do numbers 2 and 3 and you write those equations out, do those in context. Moving on. Okay, on this page, page 7, I wanted to point out to you which is the x variable and the y variable because I think it could go either way. So we're going to have a discussion and we're just going to set it. We're going to say that you've got this fast food and you are wanting to predict your calories from the fat grams. So if I'm predicting calories, which one's x and which one's y? Fat's x, calories is y. That's going to play into your part A, which asks you for explanatory and response variables. Now, I wanted to talk to you calculator-wise about part D. Part D asks you for x bar, y bar, s of x, S of Y. So those things you can get from doing a one variable stats for list 1 and a one variable stats from list 2. But have you ever wondered what two variable stats is? Two variable stats will do that list 1 and list 2 for you simultaneously. So if you do two variable stats, and I don't have this correct information. I have old information in here, but I'll just demonstrate. If I do two variable stats of list 1 and list 2, do you see how it gives me X mean and X standard deviation? And then down lower, it gives me the Y bar and the Y standard deviation. So by doing two variable stats here, you can do that all together instead of just doing one variable stats for each list. Okay, questions there. How are you going to get these things? Where are you going to get all of these things come from? In your calculator, you're going to do what? Linear regression. Good. Okay. Don't forget that if it's asking for, does a linear model appear to be a good fit? Then, based on the residual plot, do you think the least squares regression line is a good fit? So they ask you for the actual residual plot over here. Draw a sketch of it. That means in this section, they just ask you for a basic pick of the raw data. Not residual plot yet. Okay. All right, so I think that's all of that. Now turn over to the next page and let's look at problem number 5. All right, so on this problem number 5, we've actually done this before, but it has been a long while, so we want to have this different kind of information, not a computer printout and not data points, and we still got to find the equation of the line. So here's a third way that you could be given some information to find the equation of the line. Here we go. Becky's parents have kept records of her height since she was born. The data set consists of Becky's age in months and her height in centimeters. The summary statistics are provided below. So the mean of age and the mean of height, which one do you think is explanatory variable? Age. Yeah, because I think age is probably going to be explaining the height. So I'm going to say that the average age is my X bar, the average height is my Y bar. That means the standard deviation of the age is my S of X, and the standard deviation of the height is my S of Y. The correlation between age and height is 0.86. That is the correlation coefficient. That's the R value. Now, this first problem says find the equation of the least squares regression line, and you have to show your work. You have got to figure out an equation just based on that information that they give you. So we've done this before. What do you think you need to find first in the equation? What? Well, what two things are you going to eventually need to find to have the equation? Slope and Y-intercept. So guess which one you're going to find first? You're going to find slope. Okay, so anybody remember how to use this data here and find slope? Okay, there is a formula. So I'm going to show it to you on the formula chart. Actually, you're going to hunt and find it. So here we go. Here's formula chart. Okay, front of the formula chart. You got your column on the left. Column on the right is all the probability stuff and binomial and all that expected values. This column on the left basically has one thing we're going to ever use, and it's the formula we're hunting for. So let me zoom in here, and let's see if you can find what I'm looking for. Here I'm going down. Tell me when I get to the slope formula. Ah, good job, right? Here is the formula for slope. So that's your correlation times S of Y over S of X, and that will give you slope. Do you see where that's located on that formula chart? Okay, it's down there. I'll zoom back in. So there is that thing right there. R times S of Y over S of X, which makes sense. Because it's that variability in the Y's over the variabilities in X's, just like change in Y over change of X, and times how well they're correlated. Okay, so I think that makes sense. So you will find that first. You have to find the slope, and then after you find the slope, you have to use a point that is on the line. What is a point on the line? Aha! X bar is the mean of X, and Y bar is the mean of Y. And that mean point is a point that is on the line, So I'm going to use Y bar equals MX bar plus B. I've got Y bar, I've just found my slope, I've got X bar, and what am I going to get from that? Solve for Y-intercept. That is how you get that equation of the line based on that information, okay? We haven't done that a ton, but you need to remember that. Okay, so there was your quick review on that, and we've got one last little review on page 10, and then I'm going to let you work. Here we go. Page 10. So on page 10, we've got computer printout for the price in dollars and the power in cold cranking amps of automobile batteries. All right, so the first question I ask you about is to give statistical evidence as to whether or not there is a linear relationship. So statistical evidence of a linear relationship means you have to have a what? P-value. So let's first define what the slope is. So what is the slope of this problem? Or beta. Beta is the slope of the relationship between what? Cost of the batteries and the power of the batteries. Okay? What will our null hypothesis be? No linear relationship means beta is 0. Alternative hypothesis. Okay, now, first period, blipped out beta is not equal to 0, and then somebody said, wait a second. We want to know if more expensive batteries are related with a higher starting power, better starting power. So what if higher cost means higher starting power? What is that kind of relationship? Not just not equal to, but what? Yeah, positive extra. As you get bigger in the X direction, you get bigger in the Y direction. That's a greater than, so that's a positive slope. So I'm going to go with the fact that the wording here asks to see if the slope is positive. Okay? Now, I've not done the whole problem with you. I've just gotten you started. What you're going to look at to determine if there is statistical evidence of a relationship, of a linear relationship. You're going to look at your p-value, and then you're going to write it out there. Okay? So I'll let you do that. What does number 2 ask you to do? Interpret this S of B. What is S of B? Standard deviation of the? Not residuals. B is the standard deviation of the slope. Standard deviation of the slope. And so you're going to sing the, if you sample many times, I'd expect the slope you find of the relation between X and Y to vary this much on average over time. What is S of E? That's the little errors, standard deviation of theirs. That is the standard deviation of the residuals. The average amount that the actual Y value point varies from what's predicted to become, varies from the predicted Y. So in summary, in class and for homework, you're going to do 6 through 8, save 9 for tomorrow because that's just a blank page, and do page 10. questions? Yes, ma'am.